In this section, we're going to take a look at what the idea of something called a local linear approximation is. And then from there, we're going to talk about these animals called differentials. A local linear approximation is essentially going to utilize the idea of a tangent line to be able to approximate the value of a function that might not necessarily be easy to deal with. And this is used a lot of times in computer programming to be able to expedite programs that might utilize difficult functions to be able to approximate or something of that nature. And being able to find the equation of a tangent line around that point can expedite and optimize the efficiency of that computer program. The idea behind it is that we have a function. So let's say we have this function, f of x equals the cube root of 3x plus 2. And let's look at it around the point 2.2. And what we notice is that the tangent line at this point, and again, this is about the point 2.2, so that would be right about here. If we keep zooming in on the function around that point with our tangent line, it looks like the closer we get to the point 2.2, it looks like that the tangent line is actually kind of converging to the exact same behavior of the cubic function, or the cube root function, excuse me. Now, it doesn't have the exact same properties, and there's going to be some error, especially the further we start getting away from that point 2.2. So what we'd like to do is we'd like to stay around that point x equals 2 to get a pretty decent approximation. All right, so essentially what we're going to do is we're going to find the equation of a tangent line, and then that's going to represent the function around that point. Okay, in this case, we have x equals 2 for us. All right, and that's the whole idea of a local linear approximation. Notice as we start going further away, all right, so if we look at this point, there's a lot more distance between those two, the tangent line as well as the original function. So again, the closer we can stay to the original point, which might be right about here, the better an approximation that we're going to get for our function. All right. And remember from pre-calculus that this is our equation, y minus y naught equals mx minus x naught. And what we could do is we could just add y0 to the other side, and we get y equals mx minus x naught plus y naught. And so that's where we're getting this formula or this function, that the local linear approximation, which we're going to call L of x. So this is our local linear approximation, is going to be equal to the derivative at the given point, x naught, x minus x naught plus y naught, right? So let's take a look at a couple examples as to how we can try to utilize a local linear approximation. A really easy example. Let's use a local linear approximation to estimate f at 2.9, given that we have the point f at 3 equals 2 and f prime at 3 is equal to 6. All right, so we go back up to our formula right here, and we know in this case that x naught is going to be 3, and we know that y naught is going to be equal to 2. We know that the slope at that point is going to be 6. All right, and so what we can do is we can go ahead and find our L of x. Okay. And we're going to use this formula up here, f prime at x naught, which we know is going to be 6. Okay, so that's going to be our f prime at x. So that's 6. And then x minus 3, which is going to be x minus x naught, and then plus our y naught. And then we could simplify this by saying that this is going to be 6x minus 18 plus 2, or 6x minus 16. And that's going to be our local linear approximation, right? So not too difficult to find that, all right? Really just basically some pre-calculus stuff. Now we're going to estimate f at 2.9. And all we're going to do is we're just going to find L at 2.9. So that's going to be 6 times 2.9 minus 16. And we could just use our calculator, right? So we could just say 6 times 2.9 minus 16, and we end up with 1.4. And we don't know if that's necessarily a reasonable estimate, but we do know that f at 3 is 2. So we know that f at 3 is equal to 2. And so we would approximate that f at 2.9 is approximately 1.4 because that's our local linear approximation. Now, a more tangible example, and we have a pretty simplistic function, so it doesn't really make a lot of sense in real life to do this problem, but just as a basic example as to where we might use a local linear approximation. We have a quadratic function, 6 minus 2x squared, and we're at the point a equals 1, okay, or in this case, x equals 1. We want to try to find the equation of line that gives us our local linear approximation at a equals 1. Then we're going to find the local linear approximation and approximate that at, or approximate 1.1 for our function. And then finally, we're just going to find the percent error. Okay, and we're going to use the exact value which is given by a calculator, although we really don't need the calculator to give us the exact value. All right, so let's start out by figuring out what we know. All right, so we know that x naught is 1 in this case. To figure out y naught, all we're going to do is just find f at 1, which is 6 minus 2 times 1 squared, which is 4. We need a slope. To find the slope, we're going to find the derivative. Okay, and the derivative of this function is really easy. That's negative 4x. And that means that f prime at the point 1 is going to be negative 4 times 1, or negative 4. Right? And so for our formula for L of x, now remember that's f prime at x naught, x minus x naught plus y naught. That's pretty easy to find now because we know that we have the slope, which is negative 4. We have y naught, which is 4, and then we have x naught, which is 1. So this is going to be negative 4 times x minus 1, and then plus 4. Right? Or in this case, this is actually pretty easy because now our local linear approximation is going to be negative 4x plus 4 plus 4, or that just gives us negative 4x plus 8. All right, so this is actually part A of the problem. And this is actually the most difficult part. Right? Now, we're going to use the local linear approximation to estimate f at 1.1. So really what we're finding is L at 1.1. This is part B, and that's going to be negative 4 times 1.1 plus 8. All right, and we can just plug that into our calculator. That's going to be negative 4. Get rid of all that. That's going to be negative 4 times 1.1 plus 8. All right, and that gives us 3.6. Right, so that's the approximation. Now, what's the actual value? Okay, well, the actual value is going to be f at 1.1. All right, and that's going to be, remember our original function was 6 minus 2x squared. All right, so that's going to be 6 minus 2 times 1.1 squared. And again, we need our calculator to do that. Right, so in our calculator, we're just going to do and multiply 1.1 and we're going to square that number. We're going to multiply that by negative 2. And then we are going to add 6 to that. All right, and so we end up with 3.58. Now, this is the exact value. And that's pretty good, right? Because if we look at those two values are pretty close to one another. And the question says, compute the percent error. Okay, so to find our percent error, we're going to take the formula. We're going to have the approximate minus the actual. And we're going to divide that by the actual. And we're going to multiply that by 100%. Right, so in this case, to find our percent error, that's going to be the approximate is 3.6 minus 3.58. And then we're going to divide that by absolute 3.58. And we're going to multiply that by 100% when we're done. So let's just do that in the calculator really quickly. So, and we could just ignore the signs at the end. So we're going to have our 3.6 or 6 minus our 3.58. Right, and then we're just going to divide that by our 3.58, which is the exact value. And then we're just going to multiply that by 100. Okay, and that's going to give us our percent. So our percent error is 0.5586. It's really small. Okay, so the percent error is going to be 0.5586592%. All right, that's a really small percentage. All right, so you can see the power of the local linear approximation, and this is much easier for us to work with, okay, than the quadratic, although both of them are fairly easy to work with. So in our next video, what we're going to do is we're going to expand upon this, and we're going to look at a little more difficult sorts of functions.